Okay, now we consider some applications of the Riesz representation theorem in PDEs. So let's consider a very simple PDE. So let's say that we have a set omega that is open bounded domain. And also we have a function that is L2 integrable on omega. And then we define the following PDE, which is or incomplete. We should say that we have defined a boundary value problem. It's called a Dirichlet boundary value problem. Of the Poisson equation. So the problem itself contains two parts. One part is the PDE. The other part is boundary value. So the PDE is the Poisson equation, which is this. And the boundary value is that the U, let's say for simplicity, we first consider the case where U is 0. So inside the omega, the U must satisfy this PDE in the first row. And on the boundary of the omega, the U is 0. So we're looking for a function U defined over omega such that the negative Laplacian of U is equal to F, where this F is given. And on the boundary, this U needs to be equal to 0. Okay, so this is the very basic but very useful PDE, and the full name is like this Dirichlet boundary value problem. Okay, so there are other type of boundary values. For example, instead of having this, you may consider the so-called Newman boundary condition, which is given by this. So what this means, what this means is this is actually the du, or the gradient of u, which is the gradient of u. It's just a stack of the partial derivatives. Okay, times the outer normal. So what that means is, so you have omega like this, 0 omega, and for each point on the boundary, this is the normal direction. Okay, it's the unit vector that is perpendicular to the tangent line at each point. Okay, so you take the inner product of the gradient of u and the outer normal vector, and then it is 0. This, if you replace this boundary condition by that, then it's called the Newman boundary condition. So it's also called the Newman boundary value problem. Okay, there are many other types of boundary values that can be imposed for PDE, but for this Poisson equation, the most popular ones will be this one, the Dirichlet one, or Newman one, or the mixed of the two. Okay, that's our commonly seen PDEs, or boundary values. Okay, so our question right now is to, well, you might wonder that when we see a PDE, probably you'll be interested in like finding the solution U that satisfies this, right? You find this U that satisfies both. But it turns out that this is a major topic in classical classical theory of partial differential equations. But soon later, people realize that it's really difficult to find an analytic solution, or to find this U, or the expression of this U, such that it satisfies the given PDE. That is almost hopeless, right? For slightly more complicated PDEs, there's just no way to find a solution. Okay, and that's pretty. That's actually within expectation, because PDEs are generally much more difficult to solve than the ordinary differential equations, or ODEs. And even ODEs, people realize that for a large class, or for almost all the ordinary differential equations, we don't have an analytic solution. Then we have to rely on the numerical solution to solve them. And it's also the case for partial differential equations. In most of the cases, we don't really have an analytical solution. We don't really have a way to find out the expression of the u in X so that it can satisfy the conditions here. But instead, we may try to find a numerical solution for that. So that is a totally different topic, and that is a major research area, or or major topic in numerical analysis or numerical partial differential equations. So what is left for the PD theory? Well, in PD theory, what people, or even for mathematicians who work on pure PDEs or pure mathematicians, they are mostly interested in the existence and the uniqueness of a solution. So what they are doing is, say, we're given a PDE like this one, and it has a certain boundary value. And the question is, does this PDE have a solution? And if it has a solution, if the solution is unique, these are the major research topics regarding PDEs. Okay, so it doesn't help us to tell what is actually the solution, but it tells us if there's any hope, or if the solution even exists. Okay, so what we're doing here is to also show that not finding the solution of the solution to the PDE, but we're trying to prove that such a PDE has a solution, and the solution is unique. And that is a very easy or very elegant application of the Riesz representation theorem. Okay, so let's see what we can do here. First of all, it is usually, when you see this Laplacian here, you know that Laplacian u is equal to, as we showed last time, this is the partial u partial x1, and the second order partial derivatives, all the way to du dx n squared. Okay, so at least you can see that u needs to be differentiable, at least twice differentiable, with respect to each of these variables. Okay, so that means u should be at least twice differentiable. And if this f is continuous, you probably want this u to be in C2, which means it's twice continuously differentiable. Okay, the second order partial derivatives are also continuous. You'll be hoping for that. But in reality, what happens is that even this f is continuous, we probably cannot find find such a u. Okay, you don't have a u that is in C2. Well, in this case, people will usually step back a little bit. Let's say that if there's no way to find such a u, then let's consider the PDE from a different angle. The PDE is given by this Laplace u, negative Laplace u is equal to v, is equal to f, where this Laplacian, remember that the Laplacian is actually divergence of du. So essentially this. Okay, we know that it's also written in this way, where this is called nebula. This nebula u means the gradient of u, and this nebula dot means the divergence. So you can also write it in this way. You can see both very common in books or research papers. Okay, so that's what another way to write the Laplacian. So now let's look at this one. If this is true for every x, so what that means is this This is true for every x in omega. For any x in omega. Okay, so if this is true, then I multiply both sides by arbitrary function. It is supposed to be true as well, right? So this implies that when I multiply Laplace u by some function v, and on the right hand side I multiply f by some function v, this should still hold, right? And when I multiply, after I multiply the v, I can take the integral on both sides. So I actually have the integral for negative Laplace u times v equals to fv. Okay, and this should be true. Okay, this should be true for any v, and this should be true for any v. Okay, then the v is also omega, from omega to r. Okay, so let's say that this v is continuous. And it is 0 on the boundary. Okay, it's continuous and 0 on the boundary. Okay, now we know that this is, if you view as a solution to this Poisson equation here, then this should be true for any v in here, right? And now what we can do is do the integration by part, because this one here is equal to, let's split the on the right out of this Laplacian. This should be negative of divergence of u times v. Okay, or if you like, you can rewrite this as divergence of du. Okay, either way. Well, I choose the way I wrote in the first line. Then this, due to the part, we can apply integration by parts, and you know that this, so this is dx. Now this is equal to the du times n times v dx partial omega minus the du. Sorry, here this is negative, so I should have negative and plus because of the negative here. Okay, and this is du dv dx. Oh, sorry, here it should be sx to be specific, because this integration is on the boundary of omega. Okay, so this is just simply applying the integration by parts. Then we will get this. Okay, this is from calculus, multivariate calculus. Well, then you look at this one, when the v is 0 on the boundary, as we said, this part will be completely 0. Because no matter what this one is, actually, by the way, this one is actually the du dn, right, as in the Newman boundary condition. But whatever it is, the v is 0 on the boundary, so that's why the whole thing will be just 0. And that is why the negative, this thing here, is just equal to this. Okay, so this implies that the gradient u times the gradient v dx should be equal to the gradient, should be equal to the integral of fv dx. Okay, so what we have done so far is we said that if u is a solution to the PDE, to the Poisson equation, then this should be true for any v in this. Okay, and it is pretty easy to show that this one is dense in this space. Recall what this one is. This is the Hilbert space, this is Sobolev space, where the v has weak partial derivative, first order partial derivative. The v has v itself is in L2 of omega, and the v also has a weak derivative. So I should write as dv, sorry, that is also in L2. And also V is 0 on the boundary. This is what this set is. Okay, and this one is dense in this set. So if this is true for any V in C0, it must mean that it is true for any V in this H01 as well. So in this case, what we want to do is, instead of looking for a solution that U is in here, we're trying to look for a U that is in a general class, in a larger class, where we only require the gradient of U exist, or even just require the weak derivative of U exist. And in this case, the U is a solution to that only if this is true for any V in this space. Okay, so if U satisfies this for any V in the H01 space, then we're looking for the U that is in H01 omega such that this one holds for any V here. Then we see the U is a weak solution. Okay, so of the PDE here, so that's PDE including the boundary value. See, that's why we require this U to be 0 on the boundary. PDE if the integral of du, dv, dx is equal to the integral of fv dx for any v in H01 omega. Okay, so we call this the weak solution. And sometimes it's also called generalized solution. And this is in comparison to the C2 solution for this original problem. That means you really can find some function u in C2 such that this one holds, and also this holds. Okay, and in this case, you call the u a strong solution or classical solution because it's like the solution that we want in the classical sense. It actually satisfies this. And this is only a weak solution. Okay, so one thing you know is that if the solution is a classical solution or a strong solution, then it must be a weak solution as well. But it's not necessarily true in the contrary. If a solution is a weak solution, it is not necessarily a strong solution or classical solution because you only require u to be in here. So that means the u is not necessarily differentiable. The gradient of u does not exist in the classical sense. It's gradient of u only u and gradient of u may only exist in the L2 space. Okay, so that's the difference. So you can see that we stepped back a little bit, and now we're looking for the weak solution. Well, what's the benefit of doing that? The benefit is that we are searching for a solution in a much larger space, so we have more chance of finding a solution. Okay, or not just in theory but also in practice, there is probably more chance to find a solution. And what is a common strategy in modern PDE is that we first consider the existence of a weak solution for PDE. Then once we found this weak solution, we can try to prove that this weak solution has certain type of regularity, which means that we can actually prove that the u or the gradient of u exists. In this case, we say that u is sufficiently smooth, and in this case, we probably can even show that the weak solution is indeed a strong solution or classical solution. Okay, so finding the weak solution, and then eventually try to show that the weak solution is also a classical solution, if ever possible. This is the common strategy in modern PDE theory, okay, to show that some solution exists. So in this case, you can imagine that showing that the weak solution exists for PDE is the first step, is also the most important step. Okay, and now we are trying to use the Riesz representation theorem to show that this weak solution actually exists and it is unique. Okay, that's our goal right now. Okay, so let's see how do we proceed with that. First of all, let's consider let's again consider this 0, 1, H01 space. Okay, and then remember that we proved in the by the Poincare inequality, we show that if you have two functions in this space, say for any u and v in this space, we're going to define the inner product of this by the gradient of u times gradient of v dx. Okay, so u and v are two functions in H01 space, and this inner product is defined in this way. Remember that uv are 0 on the vanish on the boundary. So by Poincare inequality, we know this is actually an inner product. Okay, we can actually show this pretty easily. Recall that the Poincare inequality tells us that any u in the H01 space can be bounded by the some constant that only depends on the omega, and the order, which is 1 here, times the gradient u squared dx. Right, we prove that. That's Poincare inequality. And we can generate an inner product out of this norm using this by showing that this norm actually satisfies the parallelogram identity, and with that we can claim that this is the actually inner product. The next step of this is we want to show that this this H01 space is complete under this inner product, which means that we want to show that this H01 omega and this inner product with this norm defined here is complete. Okay, we want to show that. Okay, to show that, we just need to show that it is equivalent to the well, actually, we already. By the way, well, sorry, I should say that we already showed that this is true. This inequality is true, and on the other hand, this must be larger than this one. This one itself. Okay, because this one here is by definition the integral of u squared plus the gradient of u squared, and then 1/2. Okay, so that means the integral actually contains this one. So that's why this is this norm we defined here, or this inner product defined here, is actually equivalent to the inner product defined for this originally for this space. Okay, so these two are actually equivalent, and that also means that this one is complete using this new norm here. Okay, so it's a complete, it's a Hilbert space using this as the inner product. Now let's consider this functional. So it's this TF for any given function f. I'm going to define a functional on the H01 space. So remember that this is a Hilbert space with the inner product that we just defined. It's a Hilbert space. And it's mapping from the Hilbert space to R. That means you take any point, which is a function right now, from the Hilbert space. I'm going to map it to a scalar. And how this one is defined, for any v, where v is in the h01 space, we can define it simply as the integral of f(v) dx. Okay, now you can see this TF is linear. Apparently it's linear, right? Because the TF alpha v plus alpha 1 v1 plus alpha 2 v2 apparently is equal to, right, TF v1 plus alpha 2 TF v2. Okay, and also it is bounded. I'm going to show that this linear functional is bounded. Why is that? Because we'll look at the absolute value, which is just this. And now you know this is less than or equal to the f v dx. And apparently you can use the Cauchy-Schwarz. This becomes f squared 1/2 and v squared dx 1/2. Okay, but this one here is equal to the norm of f, the L2 space, in the L2 space. And this one here is bounded by the one norm, because you remember that this one is bounded by h01, sorry, v h01, right? And this h01 is less than or equal to some constant times the v in the one norm. Right, this one norm is like the one we define here. The one norm of v is defined to be the one inner product between v and v itself, then take a square root. Okay, that must be less than that. So that means this is less than or equal to CF, the L2 space, times v1. Okay, so this is like a constant, we call it the m. So that's why this one here is bounded by some m times v, one norm of v. So this means that it's not just linear, but also bounded, which means that it's continuous. Okay, so that means the TF is a bounded linear functional of the space here. Okay, so this is like the X we had in the Riesz representation theorem. It's a Hilbert space, and the TF is a bounded linear functional. And this implies that the Riesz representation theorem, there exists a unique function u in h01 omega, which is also just x, such that the TF of v is just equal to uv one norm. Right? That's what we proved in the Riesz representation theorem. And now you see what this one actually means. The left-hand side, as we said, is just the integral of f and v dx. And the right-hand side is the uv1 norm. But by definition of uv1 norm, it is just this. So that is just the integral of gradient u times gradient v, the dot product, which means the inner product of two vectors. Remember that each of these two is in Rn, right? Because we're in n-dimensional space. So that's how we show that there exists a unique weak solution to this PDE. Okay, so we didn't really touch any calculation, but purely proved this existence and uniqueness using the theory of from functional analysis. So you can see that how powerful this the results in functional analysis can give us. Okay, so that is application of the Riesz representation theorem. And also you can consider a more general case, say in some cases that the PDE was not given by just simply this, but it may be given by some actual function. Say I have a PDE that also has a Dirichlet boundary condition, which means that this is still Poisson equation, but the u is said to be some function g, which is given on the boundary. So what do we do with this? And it's a common strategy. This is not the only strategy, but it's one common strategy is to try to get rid of this g. By doing that, since g is given on the boundary, as we said, on the boundary of this omega, so you try to first find some function u0. You don't care about if it satisfies the PDE itself or the Poisson equation itself. Just look at this u0 such that the u0 is continuous. Maybe hopefully it's C2 such that the u0 is equal to g on the boundary. Why we're doing this? This is because once we have this u0, we can think that the solution to this one is, we can just consider the difference between u and u0. Because in this case, when we take the Laplacian on both sides, we'll have Laplacian w equals to Laplacian of u minus Laplacian of u0. Okay, and now we know negative Laplacian of w is equal to negative Laplacian u plus Laplacian u0. But remember, this u0 is something you already obtained, so you can compute its Laplacian. And the negative Laplacian of u, we know that is equal to f, so this is just equal to this. Okay, and on the boundary, we know that on the boundary of omega, this is equal to the u on the boundary minus the u0 on the boundary. But we know that both of these two are equal to g on the boundary. So this is g minus g, which is 0. So now we obtain a new PDE, which is the same as the earlier one. It's just a Laplacian, negative Laplacian of u equal to f plus Laplacian of u0, and the w is equal to 0. This is the in omega. It's on this. Okay, and then we can just try to find this w or show the existence and the uniqueness of a weak solution to this PDE as we did before. Then with that we can just add this u0 and get back. Okay, so that is one strategy that we can use. Okay, so that's the solving of PDEs. There is also another class of problems in the theory of PDE called variational inequality. And what that is called variational so in the theory of PDE and also theory of optimization, people will be interested in a solution to a variational inequality. So for the same context we had for the PDE, we can consider a variational inequality in this context. Suppose that C a closed convex set closed convex subset of H not 1. Okay, it doesn't have to be a linear space or a linear subspace or whatever. It's just a convex subset of a H01. Okay, and also as before, F is L2, which is given. Then a variational inequality is this: Laplacian u times the Laplacian, gradient u times the gradient of v minus u omega dx greater than or equal to integral of f times v minus u dx omega for any v in C. Okay, so this is called so-called variational inequality. What that means, apparently it's a inequality. We call it variational inequality is because if we can find, we're given the f, and we're trying to find the u function u in this space. Find u in C such that the vi holds. Okay, the vi is that for this u, it needs to make sure that this left-hand side is greater than equal to the right-hand side for any v in C. Okay, that's our goal. And the question is if such a U exists, and if it exists, if it is unique, right? That will be our question interests. So the solution to this one is called U, we can denote by U star, and let's show that such a U star must exist and is also unique. Okay, how do we show that? Again, because that this as we did before, we can again think this norm is H01 omega, and this one norm. We consider this. We know that it's a Hilbert space, right? And then also for the given f, we know that for the given f, we again define linear bounded linear functional, as we did before, a bounded linear functional f that is a mapping from any v to tf of v, which is defined to be the integral of fv over this omega. And we showed before that this tf is a bounded linear functional. Okay, and that also means there exists a unique w such that, or let's call it wf because it depends on what this f is, such that this one is in H01, such that the tf of v is equal to vwf or wfv, either way, because it's a real Hilbert space, and this inner product is symmetric. So this is true for any v in H01 omega. Remember that this means that the gradient of v times the gradient of wf dx. Okay, that's what this inner product means. Okay, we know there exists such a wf. Okay, so with that, we recall the variational inequality here. We know that this right here is nothing but just this is just a tf of v minus u, right? And according to what we have for the tf of any function, this should be equal to the v minus u wf, right? Inner product, the one inner product of w v minus w, sorry, one inner product of v minus u times wf. Okay, so the v variational inequality is equivalent to this. Have the v, let's see. Okay, it's actually sorry, it's creating the this is the f v minus u, as we said, and this is equal to tf v minus u. This is equal to v minus u wf 1, and eventually this is just equal to the integral of dv minus u times dwf dx. Okay, and then we can move the right hand side to the left hand side. We see they both have this common term like this. Okay, so this means that I have the du minus dwf, or the other way I can rewrite this as d of u minus wf inner product v minus u dx greater than or equal to 0. Okay, this is equivalent to that. And this equivalent to, now you can see this essentially is the u minus wf and v minus u1 greater than or equal to 0. Okay, do you see something familiar? Remember in last class, we showed that if you have a Hilbert space X and you have a closed convex set C, and then for any X, now in this case is WF, there exists a unique projection point where U is a projection of WF onto C. And for this projection, it is a projection point if and only if this is true for any C, for any V in C. Okay, and we know this is true. This is true by the theorem we proved for here. Okay, and this is equivalent to this the existence and uniqueness of this U. And this tells us that the variational inequality here does have a unique solution, U. Okay, so that's how we prove the existence and the uniqueness of a solution for the variational inequality. Okay, again, we didn't really touch any of the calculation there, but just the following, just using the some result from functional analysis to prove the very important result for in PDE or in variational inequality. Okay, so that is another example. And this can be also extended to a more general setting. For example, sometimes we consider not just a Poisson equation, but also a more general PDE, which is given by this way: sum of I from 1 to n. Remember that n is the dimension of the omega. Okay, omega is in Rn. Okay, open bounded, and this is di. This means di of u is a shortcut for du dxi. Okay, and also similarly, when you see something like this just means that du dxi squared. Okay, just for simplicity, you can write it in that way, and then you have the aijx times djux equal to f of x for any x in omega. Okay, you can also imply do some boundary condition, which is again say this is equal to 0 for any x on the boundary of omega. Okay, so this is generalization of the Poisson equation above. So this is called the second order elliptic equation, or at least in the simple form because you only have this term. Sometimes that the elliptic equation also has some lower order terms, but just for this term, you can see that it will reduce to Laplacian u if this aij. By the way, this aij comes from the entries of a matrix or matrix valued function. Just a11x, a1nx, an1x, and also annx. Okay, so this is the n by n matrix. For every point x in omega, it is n by n matrix. Okay, and I'll also assume this A to be for every x is symmetric. It's a symmetric matrix and a positive definite. And this is not a positive, and it's actually required to be greater than or equal to this. Okay, I hope you understand this. This notation means that if you treat for every fixed x, you treat ax as a matrix, then this is a non-negative definite matrix, meaning that you multiply any vector on the two sides of this matrix, because this here is n by n matrix. You multiply some c, any vector, n-dimensional vector c on both sides, then this should be some number greater than or equal to 0. Okay, the left-hand side becomes a scalar, it should be greater than or equal to 0. This is what this one means. And this, by the way, this delta is greater than 0. It's some scalar but greater than 0. This I is a n by n identity matrix. Okay, we do assume that it's symmetric, and also it satisfies this. Then we consider that. Well, when I say this is generalization of the Poisson equation, it's because when this ax is just the identity matrix for any x, then this reduces to just the Poisson equation. Okay, you can easily verify that. But this is more general. And for this type of PDE, we can also show the existence and the uniqueness of a solution. And why is that? Well, in this case, we are going to follow the similar strategy as before, but right now, since we have this A involved, it's a little bit more complicated. So to this end, let's say we define a function B. B stands for bilinear. Let's say define B as a mapping from, it takes 2 points from H01 space. That means you give 2 functions, u and v, to help you to give you output is some value, a scalar. So what this means is for any u and v, the BUV is defined to be the sum for ij from 1 to n, aijx, gradient u, sorry, I should say du dxi times dv dxj omega. This is, remember this for every point x. Then you take the integral. This is how we define this b function. So it takes any 2 functions u and v, and you get a scalar. So it will be a scalar. Okay. So first of all, you can see that b is bilinear. It's linear in u and it's also linear in v. It's linear in both arguments. And it's symmetric. If you switch u and v, you get the same value because aij is from a symmetric matrix. So it's aij equals to aji for every x. Okay, so b is a linear, a bilinear, and a symmetric. Okay, so not only that, we want to show that the b actually gives us an inner product. So to guarantee that, we also need to make sure that the b is positive definite. And to do that, let's just look at the b. So the BUU is equal to, according to the definition, it's just the ij, 1 to n, aij, diu, dju, dx. Okay, remember what this one is. This is like the gradient of u. If you like, you can actually write it out. This is nothing but just write it out. d1u, dnu, and then the ax matrix, and then the d1u, dnu. Okay, so basically this is just the du, which is treated as a column vector at every point x. This gradient u is a vector, n-dimensional vector, and the same vector here, but I put it as a row vector here. So it's du transpose. Okay, so this is essentially just a du x transpose. For every point, this is the n-dimensional vector as I just said, and this is n by n matrix, and then this is a n-dimensional column vector. We know that the property of A is that this is bigger than equal to delta times gradient U squared for every fixed x. Okay, so that means this is greater than equal to the integral of delta, which is a scalar, positive scalar, ux squared dx omega. Okay, and this is actually delta times the u1 norm square. Remember the 1 norm, or the u1 norm is defined to be the u1 1 half. And this 1 means that the du times du, right? That's what this means. And we know by Poincare inequality, this is actually a norm. Okay, so now we show that the BUU is equal to that. It's bigger than or equal to the delta times this. Okay, so what this implies us is this is always non-negative. And also it is 0 if and only if the u is 0 function. So this implies that B is positive definite. It's positive definite. And because we have that it's bilinear symmetric, and also we show that it's positive definite, so these two together implies that B is an inner product. It is inner product of this space. Okay, now we can just say, let's just denote the inner product using this B. So we have any two vectors, 2 points, uv from the H01 space. We call this B inner product of U and V to be BUV. Okay, and this is the inner product. Okay, so with the inner product, we can also use it to define norm, right? And, the norm, the B norm of U is just equal to the square root of that, or if you like, just say that's just. Okay, so on the one hand, you know that it is this one here. We already showed that it is bigger than or equal to delta times u1 square, right? So that means this is bigger than square root of delta, the u1 norm. So that's one side that we know the B norm is stronger than the 1 norm. But on the other hand, let's say that we assume that all these entries are bounded above on this omega. Say the aijx is bounded by m for any ij in from 1 to n, and also for any x in omega. Let's say this is the case. Then we can say that this is easy to show that this is also bounded above by some constant times the u1 norm. The reason is, remember that this norm is just the integral let's say this is because when we look at the aij, some ij diu dju, this is the B is equal to BU, right? And that this is less than or equal to some, because the aij's are all bounded by m, so it should be bounded by some m. I think there's another constant somehow, maybe n, from 1 to n. But anyways, some constant times diu d, say d du times du. Okay, and then this one is just the d1 norm squared. Okay, that's how I say that this is just the b norm of u squared. The b norm of u squared is less than or equal to some constant times the 1 norm of u squared. So that constant is this c. Okay, so what we have done so far is that this norm here, the b norm here, is bounded between some constant times the r1 norm, the 1 norm of u, and also bounded above by some constant times the 1 norm of u. So that means these two norms are equivalent. This b norm and this 1 norm are equivalent. So the h01 is complete using this norm, and it must be complete under this norm as well, because these two norms are equivalent. Okay, so now we can, instead of considering the 1 norm, we can consider this with the b norm here. This will be also complete. It's a Hilbert space. Okay, it's complete. Okay, now from here we can again consider the PDE. We cannot consider the PDE now here, which is this one. We want to see if a weak solution of this, sorry, I should say that the weak solution of this exists and unique. Okay, to do that, let's consider again the TF mapping. It maps, it's a linear, bounded linear functional on this H01 space. It is defined by integral of fv dx. Okay, and we know that this one, since it is a bounded linear functional, we know that by Riesz representation theorem, there exists a unique, again called WF, in H01, such that the TFV is equal to VWF using this B norm, a B norm product for any V in H01. Okay, and what this means is this left hand side is just the f of integral of f V. The right hand side, according to our definition for the B in the product, this is just the B of VWF, right? But the B of WF, according to our definition, here or here, just this. So that is actually the weak form for the PDE, just the sum ij, aij, div, dj, wf. So what this means is wf is a unique weak solution to the PDE. WF is a unique weak solution to this PDE. Okay, so it's basically the same idea as before, but due to the complication of that, we define a new norm and show that this new norm or this new inner product is equivalent to the original one, and then we can carry out all the same derivation to show that the solution exists and is unique. And similarly, we can show we can consider the vibrational inequality, where this left-hand side, let's see the vibrational inequality here. So instead of having that, we can consider the sum of ij, aij, diu, dj of v minus u. Okay, we can replace this left-hand side by that, and this is essentially just equal to the u v minus u b inner product. And we can show that the existence of and the uniqueness of a solution to this variational inequality. And the idea is just the same as before. Okay. Okay, so that is a very powerful application of the Riesz representation theorem. Okay. Now we're going to consider also some other properties of the mappings and the Banach space some interesting properties about Banach spaces. So it's called category and also open mapping theorem. Okay. So we first give some interesting definitions. Let's say that dxd is a complete metric space. Essentially, it's a metric space. Be a metric space. Okay. Then we say that a subset E, which is subset of X, is called nowhere dense. If its closure doesn't have any interior point, if the interior point of the closure of E is an empty set. Okay, you take a closure and then you look at try to see if there is any interior point. If there's none of them, then you say this E bar this is set E nowhere dense. Okay, so examples. You have a finite set, for example. It must be a nowhere dense set because you have finite set, means that you have something like this, and then you take a closure would be just themselves, and then apparently the closure doesn't have any interior point. Okay. Also, for example, you look at the integers on the real line. The integers on the real line. If you take the closure, this will be still the integers, but there are actually no accumulation point at all. Okay, and again, the closure doesn't have any interior point. Okay, and also the control set, you can show that it doesn't have any interior point. The reason is you look at the control set because remember the control set is that you have 0 to 1 and you take out the middle third, and for the remaining 2 you take out the middle third again. So you take a closure of that, it will be still the same set because I think it's already closed, and but there's no interior point because no matter which point you're looking at, when you draw a neighborhood of it, it must contain something that is not in the set. Okay, so none of the points in the control set is an interior point. Okay, so there are some examples like this. This is called nowhere dense set. Okay. So let's look at the proposition. So for simplicity, just P proposition. We have a sufficient necessary condition for a nowhere dense set. So we have a metric space. Then E is nowhere dense. Again, E is a subset of X. Is nowhere dense if and only if for any ball in X, so the X and R are arbitrary. Okay, for any, this means that the ball centered at X with the open ball centered at X with the radius R. For any ball, there exists a ball inside this ball such that the closed ball, or the closure of this open ball, take an intersection with the E bar, or the closure of E is empty. Okay, so this is a sufficient necessary condition for a nowhere dense set. Let's do the proof. Okay. Now suppose that E is nowhere dense. So we start from here. And what that means is, by definition, the interior of the E bar is empty. Okay, so that's what this means. And also because the interior of this E bar is empty, that means the closure of E does not contain any ball, because otherwise it will have an interior point. The center of that ball will be interior point, right? So no matter what the center is and no matter what the radius is, it does not contain a ball. Okay, so this also means that for any ball like this, there must be something in this ball, but not in the closure of E. This is non-empty. Okay, so this is what we know. And now let's construct, try to construct the conclusion. Okay, how do we do that? Remember that because this is non-empty, I can choose some point, x prime, that is inside this ball, but not inside this. Right? Because it's non-empty, I must be able to find such x prime. So the x prime is inside the open ball, but not in here. And that also means that it's inside this, and the intersection of this here. Okay, now remember that this is open. Okay, this is open, and also the closure of E is closed, so that's why this whole thing is open. And now we have an intersection of two open sets. So that means this whole thing is open. And now I have x prime that is in the open set. That means there exists some r prime such that the entire ball centered at x prime with the radius r prime should be inside this. Okay, because x prime is the interior point. It's a point in the open set, so it must be an interior point. That means that's why we can find such a ball. So that's in here. Okay, so what that says is, say we have the ball here. This is the x with the radius r, and since we said it doesn't include it has some point that is not in E complement. That means the E complement maybe this E complement. E closure. So and there will be something outside, and let's say that's x prime. But since the complement of E closure is open, and also this ball BXR itself is open, so we know that this part will be open. And it's open means I can find a ball here. So you can see that if I take the closure of this ball, or at least when I take the closure of this ball with half of the radius, I'll take the closure of that, this will be still inside this x prime, r prime, right? And this means that it's inside the bxr minus E closure. This is inside this, that means it's inside here, but not inside here. That means these two this ball, we take a closure, take the intersection of this set here must be empty. Okay, this shows this direction because for any ball, we find some b x prime r prime, but just that right now the r prime is half of r prime, so that there exists some ball here in this ball, and then take the closure of this ball. I should write maybe in this way. The intersection of these two closures is still empty, and that is proof for this direction. And now let's consider the other direction. Suppose that the right-hand side is true. Let's show that E is nowhere dense. Let's prove this by contradiction. If not, then the interior of E closure is not empty. And this means that there exists X that is inside the interior point of E closure. Okay? And that also means that there exists some radius such that the entire ball, X, R, is inside the interior of E closure. Well, in this case, if you look at any ball inside this ball, because this ball with center X and the radius R, this is already inside the interior. Sorry, I should say this. If X is in the interior, means that this must be inside here. We already know that's inside the E bar. So it doesn't matter which ball you have, the closure of that must be also inside the E bar. And this is a contradiction to the statement we have here. Okay, so which is inside here, because the E closure is closed. So it contains any subset of that taking closure is still inside that. Okay. And this is a contradiction to the statement we have on the right hand side. Okay, this proves the other direction.